So last talk before lunch is by Andres and Lucas, who is going to talk about using formally verified post-quantum algorithms in large-scale deployments, and we leave it to them.
Hi, I'm Andres, and we're really here to tell you about post-quantum deployment at scale. In particular, we are looking for public key encryption for chems and digital signatures. And the context is the same that you have heard many times over here, where there is a concern for quantum computers. There are standards that mandate post-quantum cryptography to be deployed as soon as by 2026. And we're really focusing on key exchange and signatures. And we're trying to do this in an open source, freely reusable manner, where the implementations we verify and build can be deployed by anyone, by which we mean many different applications and many different social contexts. Now, the motivation for verification is a little bit more subtle. And really, the context in which it makes sense for us is that we're verifying and deploying optimized implementations. They're rather intricate. The experience from elliptic curve cryptography is that there were a number of bugs in highly optimized implementations that were found over, in some cases, years or maybe even decades. And auditing was very challenging. If an implementation consists of thousands of lines of code, it is very hard to spot a place for an index that should have been a 1 was a 0, and it's even hard to tell whether it was a conceptual error or a bug. Now, there is an argument that perhaps lattice cryptography is simpler than ECC, and for reference implementations, I buy that. You can write a simple MLChem and not that many lines of code, and it's pretty neat to review. But once you get to optimized implementations, this simplification really doesn't carry over. And there are, again, subtle things that come up. For ECC, we had carry chains. For PQC, we mostly don't have them, or at least for MLChem, we don't have them. But instead, we have delayed reductions, we have manual vectorization, and bit packing and other low-level programming tasks that, again, are error-prone in, from a far-away perspective in a rather similar manner. And I will now hand this over to Lucas, who will tell you about how we verify those implementations.
Thanks, Andreas. So yeah, let's dive into the technical details. Oh, yeah, working. Yeah, so our target is MLChem, previously known as Kyber or FIPS 203, and we implement and verify this standard. But what did we implement really? So we implemented MLChem in no SCP Rust. So that's around 16K lines of code, and it's optimized for both Intel and ARCH64. And there's around 2K lines of code for SIMD optimizations using intrinsics. It's quite easy to integrate and deploy, so you can already today use the libcrux MLChem crate. And as you can see on the table, the code is roughly divided in 4 parts. So the mathematical part with field, polynomial, matrix, low-level formats, 3K lines of code, just as mathematical. The crypto algorithms, like sampling in CPA, in CCA, that's around 6K lines of code. And then, so all of this code is generic. Then we have high-level APIs that provides MLChem with different size. And so that's 4K lines of code. All right, let's see a bit, because we want to implement MLChem, but we really want also to prove it. So this diagram explains a bit how we do for the proof. There is 2 parallel processes. First, on the left, we start with a NIST specification and write a star specification, a formal specification, which is small, mathematical, and easy to review with respect to the textual specification. On the right-hand side, we start from our Rust optimized implementation and use HAX, our tool chain, to get a functional model in FSTOR. And so now we have those 2 parts in FSTOR. And so we can conduct a proof of equivalence between those 2 parts. And with that proof of equivalence, basically what we have as a result is total functional correctness for our implementation of MLChem. We'll also talk about secret independence a bit and panic freedom. But now let's dive into an example of writing crypto code in Rust. So here we look at barrette reduction. And in this case, there is 3 small specificities we have to note. First, we can't use modulo. We need constant time. That's why we use barrette. And then we used a specific modulo, 3329. So that's something, a prime used in MLChem. The last thing is that we use, as you can see on the slide, 32 signed integer. So it's a signed Barrett reduction. Now, what does that mean to specify correctness and prove correctness for this Barrett function? As you can see here, you have like a contract with a pre and post condition. And here the post condition says that the result modulo 3329 should be basically the same thing as the input modulo 3329. So that is our lemma, our correctness for this function. And in this case, that's pretty nice because FSTAR is able to prove that automatically for us. I haven't talked about the precondition yet, though. So what, as you can see, the input is constrained in a bound. And so what happens if input is not in that bound? So even though Rust is thought of as a safe language, and it is memory safe, right? But that doesn't mean it cannot fail at runtime, panic at runtime. So here we need to make sure that the plus or multiplication doesn't overflow. If input is too big, that will overflow. So with our method in FSTAR, we can prove statically that this will never happen for this precondition. And so that's the proof of panic freedom, as we call it. And this is required for total correctness. Okay, let's look now at another example. So that's about low-level formats. So in MLChem, there is a few places we need to pack and unpack internal data structures as bytes, basically. And so here, the example is about MLChem ciphertexts, which are encoded as 16 unsigned 16 integers. And so, yeah, we can pack 2 such integers as 3 bytes and vice versa. And the thing is, here in MLChem, there is a lot of different such data structures. Sometimes it's only 12 bits that are relevant, like on this diagram. Sometimes it's different numbers of bits or different architectures. So we have a lot of variance. And here, performance is actually super important. So we need to hand optimize all of those variants by hand. And so that's actually one of the most annoying thing that has to be done in MLChem. And so if it's annoying to write as a Rust code, you can imagine that proving this thing is even more annoying, right? So instead, we wrote a tactic. So a tactic is a program that manipulates proof goal. So we wrote a tactic that takes care about proving those things for us. Another thing to look at is secret independence. As we all know, it is very important. And in our implementation of MLChem, we stick to a standard discipline, basically, and we enforce this discipline using Rust types. Note that it's quite a crude discipline. It doesn't prevent compiler-induced leaks or microarchitectural leaks. But even if it's very standard, we actually found a timing issue in our code. And this issue was present in other implementations. So here in detail, that's that we have to divide secret values by the modulus. And the author of the reference implementation were expecting this to be translated as a multiplication, but it's not always the case, right? Like some compilers don't. And that's how we ended up with Kyber/. Okay, so we've been looking at a few examples and how we prove them, etc. But really here, the issue, as you can see, the Rust code is already quite big. The FSTAR code is even bigger. So here, really, the key for our success to prove our Rust implementation was automation. So we resorted to multiple automation strategies. First, for mathematical bits, we used SMT-based automation. For more mechanized things like serialization, we could resort to SMT-based tactics. And as we saw just before, for secret independence, we actually just use a light type analysis in Rust. But still, there is a need for manual proofs and manual FSTAR annotations to tie basically all those proofs together. And as you can see on the table, the proof effort is quite distributed on the code base. All right, so now we have a verified implementation of MLChem. So you may think, oh, it's done. we are done. But actually now we need to bring this to scale. So Andres will.
So at this point, we have highly optimized, verified implementations, and we would like to deploy them at scale. And turns out doing this with a new tool chain comes with challenges that are only tangentially related to verification, but still very important. Luca told you how writing this in hacks and Rust helps the verification process greatly, but it also means we end up with verified Rust code, and many consumers of crypto libraries can only accept C code. So there is an entire third parallel process for how this Rust code gets interpreted and translated to C. The translation itself is very simple, but really the challenge here is supporting C code for all deployments that need it. And it has already been deployed in NSS and OpenSSH and Signal and so on, and we're looking at more deployments still. There are simple challenges, such as if you start with Rust code that is generic over which MLChem variant it implements and is proven generically, you then need to specialize it for C code because C does not have Rust-compatible generics, and this results in code size increases. For the optimized implementation, we saw a 40 kilobyte size increase in the library compared to a naive tiny reference implementation. Then a number of crypto libraries already have MLChem, often reference implementations that use a simple representation for their types. And then if you want to replace the array of uint16s with an array of ABX vectors, you suddenly realize that the alignment requirements are different, and there is software engineering work to be done there. There is also questions with types in C, like strict aliasing. If you have an array declared as one type, can you store in another type in there? And so on. Also, just trying to compile this translated code base with every compiler that our crypto libraries are used with is a lot of work. Some of them only accept C++. You would think that C and C++ are the same language, but no, they're subtly not. If you want to return a struct of unions, initializing that before C++20 is a special incantation. And overall, we support about 100 build configurations. And this is a growing number. I'm intentionally not giving it as exact here. And this includes things like big endian machines and weird Apple architectures with ARM and so on. And we're trying to do this in a manner where this work can be continued and maintained. So we talked about formalizing the specification. This specification would be what crypto library maintainers review, and the code generation would be checked by the proof. Now, to do this in a manner that actually fits into software development life cycles, we would want the proofs to be checked on continuous integration and the implementations to be generated there, and this has been achieved. And the technical side is in a relatively good shape. We were also hoping that Crispin will continue providing long-term support for both the toolchain and the implementations, which means they can survive in the future, perhaps as new variants are added or so on. And even though all these steps, even from a library maintainer's perspective, they're a lot of work, there is a great argument for doing this work, which is that we provide much better performance than reference implementations. It is roughly a ballpark 2x number from our prototype integration into Boring SSL. And just to sum up everything we said just now, PQC is coming. Verification is important to get high quality implementations. We demonstrate this with MLChem with a number of deployments already. This verification effort did find a bug in our implementation and others. The steps from a fast verified implementation to a fast verified and widely deployable implementation are a lot of work, and it is especially a lot of work when we're doing it first time for a specific tool chain. But fast code is desirable, people want it, and at scale deployments are happening already. We're looking for more of them, and then once we finish with MLChem, we will look at the MLDSA. For most applications that are not as demanding as the very demanding applications we have looked at, the Rust and C code we produced are already available, and you will likely have a good time using them. Thank you.
Thanks for the very interesting talk. Very, very important work. Very, very cool work. How fast is the generated C compared to Rust? I was wondering if it's like, have you had a chance to benchmark it?
The answer is that we don't know from the top of our head. Based on how the process works, we would not expect significant differences.
Cool, thanks.
Hi, nice talk. And I have a few questions, like what's the challenging part of the Rust implementation compared to the C implementation? Or you just like follow the C implementation paradigm, like use different syntax like the Rust syntax. What's the challenging part? This is the first question.
Thanks for the question. Do you mean in this tool chain that transform Rust into C specifically, or?
No, I mean you mentioned the Rust implementation, some details like Barrett implementation, you put some code of it. I just want to know what's the challenging part, or you just like use a different syntax for MLChem, like using Rust.
So I don't exactly know how to answer your question. Do you have any idea, maybe?
I've seen independent implementations in Rust and in C++ templates, so roughly the same logic. And at high level, it is similar. In fact, it would seem that Rust and C++ are both more friendly to MLChem implementation than C.
Okay, I see. And also, I saw the benchmarking results you compared to Bo-Yin SSL on AVX2 implementation. So do you also compare to the existing AVX2 implementation, like the C, with AVX2 one, yeah.
I would recommend you to look at Crispin's blog. There are numbers there. I don't remember for sure which specific implementations are listed.
Like okay, I see. Thank you.
Hi, thank you for the talk. I'm Nicola Tuberi from Tampere University. I have one question and one comment. The first one is a question about your line there, next up MLDSA. Do you have a timeline for when you will work on that?
Yeah, so I think the whole project was 6 months. I think, or 6 months of proof, I think, and something similar for implementation, if I'm not mistaken. Maybe I am.
Okay. So it's coming soon?
Oh.
For MLDSA, I think work has already started and there is substantial progress. Yes, I think the expectation, I would expect time scale of months here.
Okay. And the other one is something that we might follow up offline, but at Tampere University, we have been working on an integration of actually your MLChem implementation in OpenSSL through our provider, so maybe we can discuss that.
We are currently working on integration into Boring SSL. The integration there would hopefully be also usable in OpenSSL, but every time we add a new target, there can be new challenges, so I'm not going to make any strong guesses here.
Okay. Yeah, thank you.
I don't see any. Is there another question? Okay, I don't see anybody else as a mic, but somehow this shows that we have time. One question, which is, what is wrong with having like written high-speed implementations and then verifying them? I understand that Amazon is having a project like that, and might not that end up being faster in both code and man hours?
So do you mean, I'm not sure I understand your question. Do you mean like, was Rust, using Rust making us able to have like very good performance, or?
Yeah, I mean, like you don't mention how fast is this code compared to the current state-of-the-art AVX2 code, but it's presumably not faster. And like I understand that Amazon has state-of-the-art AVX code, which they verify to be correct. I mean, like, wouldn't that just work equally as well?
I believe there is an additional angle here, which is the software engineering lifecycle management of this code base, where handwritten assembly code tends to be very challenging to maintain. And if we have Rust where proofs are simplified by the fact that safe Rust corresponds to functional programming, it is hoped that future changes there would be easier. I agree this other avenue is valuable, and especially if you're going for the last few % of performance, this might be what one might do.
No more questions. Let's thank Lucas and Andres